Today we're going to start the first of your grade 12 work, namely sequences and series. But before we start, I'm going to just quickly give you a summary of what we know at this stage. At this stage in grade 11, we have learned that we have a first difference that's constant, and we used to work out the formula using Tn as An plus B. And we have what we call a second difference that is constant. And we would work out the formula to generate the terms as Tn is An squared plus Bn plus C. Now, I want you to stop for a few minutes and quickly recap what we know, and then we can go and have a look at an example or two from last year, just to refresh your memories. There are many ways of dealing with this. In fact, we are going to end up doing this because its proper name is an arithmetic sequence. And the proper name for this one is a quadratic sequence. Now, I'm going to stop for 2 seconds just to show you something that's very interesting. If we take this first term, term 1, and we replace every n with 1, we're going to get that, plus that, which then is going to give me A plus B plus C. If I go and work out term 2, well, that means go along and wherever there's an n, put a 2. And if I do that, I'm going to get this looking at me. And of course, I would get 4A plus 2B plus C. Let's work out 2 more terms, and then I'm going to show you something that's very useful for when working with these particular terms. So it's A, 3 squared plus B times 3 plus C. And if we tidy that up, we're going to get 9A plus 3B plus C. And one more term, term 4, is going to be A, 4 squared plus B times 4 plus C, which gives me 16A plus 4B plus C. Well, that's quite interesting, because now what have I got? I've got A plus B plus C being my term 1, 4A plus 2B plus C being term 2, and 9A plus 3B plus C being term 3, and 16A plus 4B plus C being term 4. So that's term number 1, term number 2, term number 3, and term number 4. So right, what do we do normally? We would look at this and we'd say, let's get our first difference. Well, if I'm moving from this term to this term, I'm adding 3A plus B on. Likewise, if I'm going from this term to this term, I'm adding 5A plus B. And if I'm going from this term to this term, I'm adding 7A plus B. We can see that this first difference is not constant. Now, if it's not constant, we need to go further. So let's see what happens on the second difference. So just to recap, that's our first difference. And we see it's not constant, not the same. And so therefore, we need to look at the second difference. So doing the second difference from 3A to 5A, it's 2A. The B is already there. And from 5 to 7 is another 2A. And yes, we see that the second difference is constant. Now, you might say, what are you doing here, Lee? Well, what I'm trying to do is show you a really nifty way of solving any of your quadratic equations. Now, what you need to remember from what I've just shown you is the following. You need to remember that if I know the second difference, it will always equal 2A. The first of the first differences equals 3A plus B. And the first term is A plus B plus C. Now, knowing those few little formulas can make all the difference to you doing the first of the questions. So let's go across to the first of my questions. Okay, it tells me the first 4 terms of a sequence are 1, 10, 25, 46, etc. Write down the next 2 terms. So let's have a look. We've got 1, 10, 25, 46. So let's see what's going on. If I'm moving from 1 to 10, I'm adding 9. If I'm moving from 10 to 25, I'm adding 15. And if I'm going from 15 to 46, I'm going to get 21. Now, we can't see any pattern yet, so let's look at the next difference. From 9 to 15 is 6. From 15 to 21 is 6. So now, knowing that, I know that this next one must also go up 6, so this would be 27, which means if I add 27 to 46, I'll get the next term. So 27 and 46 is 3, carry the 1, 73. And now I know that to get the next one here, I'm going to increase by 6, so this is going to be 33. And again, to go on from here, I know that 33 onto that is going to give me 106. So there's my next 2 terms. Quite simple and quite straightforward. Now, what I'm going to do next is I'm going to work out the Tn. Now, what I've just shown you is a really nifty way to know that. What did I say to you? I said the second difference is 2a. The first difference is 3a plus b. And the first term is a plus b plus c. So let's have a look what that means. That means that 2a would equal 6. Now, if that was so, do you agree with me that the a would equal 3? Because what I would do is I would divide both those sides by 2. Right, now if I go to my first difference, I know that 3a plus b will equal, and my first difference is 9. However, I know that a is 3. So I'm going to go 3, replace with 3, plus b equals 9. So that's 9 plus b equals 9, and so b is 0. So now I've got my b value. So I've got a, I've got b, and the last remaining thing is to find my first term. Now what do I know? I know that my first term is 1. So I'm going to say 1 equals a plus b plus c. Now, I know that a worked out to be 3, b worked out to be 0, and I've got my c. So if I want to work that out, the c is equal to minus 2. So right, what do we know? We know the formula is Tn is an squared plus bn plus c. So the formula would be Tn equals, the a would be 3n squared. This would be 0, because it would, well, let's write it in so you can see it, and the c is minus 2. So that becomes 3n squared minus 2. Right, let's check if this is the correct formula, because obviously we need to make sure about that. Once you get comfortable with this, you won't need to even do that. So let's say I want to work out the 4th term. Well, what would I do? I'd say it's 3 times 4 squared minus 2, which would be 3 times 16 minus 2, which would be 48 minus 2, which would give me 46. Let's see if that's correct. Yes, it certainly is. There it is. My 4th term is 46. Lovely little method. There are other ways to do it. There's a way that requires you to find T0. And basically what you do is you'd work back one more term. But I think this is relatively straightforward and easy to remember. Let's have a look at one more just to be sure we're all right. Okay. This is an interesting question, because if you look at it, they're asking you to find the 40th term of the sequence. But if you look at it, it's not behaving nicely. If you look at every odd term is working out to be 3. So this is term 1, this is term 3, this is term 5, this is term 7. So every odd term is 3. So if I'd asked you for the term 39, you would have been easy. You would have just said to me 3. However, I'm asking you for an even term. And if I look at the even terms, they are doing something very different. Now, this is a lovely problem-solving kind of question. So what I'm going to do is I'm going to take just the ones I'm going to work with, which are the even ones, and I'm going to say to myself, in actual fact, the 40th term of this sequence is the 20th term of this other sequence, because we know in between these are all these 3s that they're putting in. Right, so let's look. If I look at the first difference, from 6 to 17 is 11. From here to here is 17. From here to here is 23. If we take the next difference, that's 6 and that's 6. So you can see our second difference constant. Therefore, we know it's quadratic. And if we know it's quadratic, we can use those 3 little formulas that I've given you to make life a lot easier. So what do I know? I know that the second difference is equal to 2a. The first difference is equal to that. And the first term is a plus b plus c. Right, so there I have 3 little equations, and what I'm going to do is work from left to right solving them. So over here, do you agree with me that the a is going to equal 3? So right, if I go to this one now, I'm going to say 3 times 3 plus b equals 11, which means 9 plus b is 11, which means b is 2. Over here, I'm going to say a is 3, b is 2, and I have to find the c. So 5 plus c is 6, which means c is equal to 6 minus 5, which is 1. So here we have a, b, and c. Right, so now the formula goes Tn equals a n squared plus bn plus c. And you can see that's a relatively quick and painless way of getting that particular term. All right, so now in the light of what we've done before, we need to go back for a few minutes and talk about the other sequences. At the end of this session, in fact, the end of the next session, because we're going to spend 2 sessions on sequences and series, I'm going to give you like a flow chart that enables you to easily find what to do, because this all becomes pretty complicated when you've got so much looking at you. And if you've got it clear in your mind how you go about selecting which kind of equation you're working with, then it's not so difficult at all. So let's go back to a blank page where I can spend a few minutes just talking about various aspects. Right, now you do have a formula sheet. And I must be honest with you and say that I have hesitation over a formula sheet because I think it slows you down. I think it causes you to sort of like scrabble around all these formulas and find out what's going on. The best place for formulas to be is here, and the formula sheet is actually only there to help you if you should forget. That way you can speed yourself up considerably instead of looking on the formula sheet. The formula sheet itself is also not very user-friendly. It's got some pretty mean-looking formulas on it. So I'm going to try and teach you without the formula sheet, and then at the end I will pull up a formula sheet and I will show you how the formulas looked, and you can decide for yourself if you want to go scrabbling around looking for formulas. Right, so let's talk about what we're going to do this year. Having mentioned very quickly what we did last year, let's now have a look at this year's work. Now, in this year, we are going to concentrate on 2 types of sequences. The first one is the arithmetic, and the next one is the geometric. Now, arithmetic have what we call a constant difference. These are the ones we were doing in grade 10 and in grade 11, where we had the first difference constant, and we called them linear. But this year now imposes a whole lot of really interesting formulas that make life exciting. So, for example, something like this would be considered a arithmetic sequence, because if you look here, if I'm moving from there to there, it's 3 units up. From here to here, it's 3 units up. From here to here, it's 3 units up. Or something like this maybe. And if you look over here, I'm going down 4, and I'm going down 4, and so on and so forth. It would actually be nice if I had one more term, just to be 100% sure that nothing's going to change. But you can see that there is a constant difference of that. Now, how did we find this constant difference? What we did is we said the difference equals term 2 minus term 1, or term 3 minus term 2. And of course, that would have to be the same answer in order for it to be a constant difference. Right, geometric, we have what we call a constant ratio. Now, I personally believe that it's better for you to work with these 2 sequences simultaneously, because they're not different. The formulas are different, but what happens is not different. The fact that we're working out a term, no matter what we're looking at, doesn't make a difference whether we have arithmetic or geometric. So looking at a constant ratio, an example of that would be something like this. Now you can see if we're adding here, it wouldn't work. We'd go up by 2, then we would go up by 6, and then we'd go up by 18. And even if we went and found the second difference, we probably wouldn't have got anything valuable either. So what we need to do is see what else we're doing. What we're doing here is we're timesing by 3. When we multiply by 3, we get 3. 3 times 3 gives me 9. 3 times 9 gives me 27. So that is what we call a constant ratio. And by the way, just to help things along here a little bit, we assign the symbol D to this one, and we assign the symbol R to that one. Right, so what are we talking about? Let's do another one. Let's say I've got 16, 8, 4, etc. Well, what's happening when I move from here to here? Well, I'm actually multiplying by a half. You could also say I'm dividing by 2, but it's actually easier to think about this in terms of multiplication. So if I look here, I'm also multiplying by a half, and so if you wanted to, the R would equal a half here. All of these are geometric. And if we're going to find our R value, we're going to say term 2 divide by term 1, and it has to equal term 3 divided by term 2. Right, so now let's talk about how we're going to start finding the first of the formulas we're going to work with. And really what I'm going to do here is to spend some time showing you what's going on. Now, if we look at this one, we always use the symbol A to represent the first term. One thing we can say about mathematicians, we're very unique. The first letter of the alphabet represents the first term. So let's have a look now and see how that works. So let's take the first one, 1, 4, 7, and 10. If I write them like this, term 1 is equal to 1, term 2 is equal to 4, term 3 is equal to 7, and term 4 is equal to 10. What am I doing? Well, over here, I'm saying term 1 is actually just the A value. To get term 2, I went and I took 1 and I added the difference 3. So it was A plus a difference. To get term 3, what did I do? I took term 2, which was A plus D, and to that I added a further D, so getting myself A plus 2D. To get term 4, I took A plus 2D, and I added a further D, getting myself A plus 3D. All right, now what is very interesting about this is you're starting to see a pattern, and maths is all about patterns. So if we look at this carefully, if I said to you, what would term 20 look like? I hope you would be able to tell me. Just give it a thought for a minute and think to yourself what it would be. Well, if I look back here, when it was term 2, there was 1 difference. When it was term 3, there were 2 differences. When it was term 4, there are 3 differences. So therefore, if it's term 20, I must have 19 differences. Right, so what happens now? If I've got term n, well, it's going to be A plus, and in place of this, I've got to have 1 less n than the number of terms. So it's n minus 1d. And this is the first of your formulas. Now, if I'm not much mistaken, I will, as I say, pull up the formula sheet. This is how they give it to you, and this is enough to scare anybody, including me. They give it like this, and then they put it equal to something over here. You can see that's basically that where they've used an I instead of an N. And I don't know about you, but I think that that's quite hectic to actually try and remember and do and work with. But it is available on the formula sheet if you want it, as I say, and we will pull the formula sheet up and have a discussion on it at some stage. Right, so that gives me my first of my formulas. Right, let's go back up now to the geometric and let's see how that looks. Right, now if I go to the geometric, I just want to get some space here. If I look at this, taking the first one, because I think it's an easier one to work with, 1, 3, 9, and 27. Term 1 is 1, term 2 is 3, term 3 is 9, term 4 is 27. So let's talk about that. Well, we know that term 1 would just be A, because we've decided to call our first term A. Now, what did we do to get from here to here? We times by the ratio. So term 2 would have been A times R. Term 3 then, we're going to take our AR, which was term 2, and multiply by a further r, giving me AR squared. And then the next one, I'm going to say term 4 is AR squared times a further r, which is AR cubed. Now, using the same sort of situation we were using on the arithmetic, if I say to you term 10, could you give me the answer? Well, yes, let's have a look up. If we look up here, term 2 has only got r to the 1. Term 3 has got r squared. Term 4 has got r cubed. So it makes sense that this must be AR to the 9, which means the formula we're going to use is Tn is A r to the n minus 1. And that's your formula for a term of a geometric sequence. Okay, now I'm going to stop at this point and go and do a few examples. And I'll slowly develop our theory as we go, because it's quite interesting watching how it unfolds. But these two formulas are extremely useful, and you will see how it actually makes life a little bit easier for us. So let's go to our example 3. The next example says, write down the next term in the following arithmetic sequence. Now, they've told me it's arithmetic. And if it's arithmetic, I know that I'm adding on a constant difference. Now, if this is term 1 and this is term 2, can I work out the difference? Yes, I certainly can. It's going to be term 2 minus term 1, which is going to be 2x plus 2 subtract 2x. Right, doing that, I'm going to get 2x plus 2 minus 2x, which works out to be 2. But you could have just looked and seen, okay, hang on a moment, to go from here to here, I added on 2. So is there going to be a problem providing the next term? No, term 3, and I don't even have to use the formula I've developed. I can just go straight into it, will be term 2 plus the difference. Term 2 being 2x plus 2, add on 2, so it's going to be 2x plus 4. Now, if I did decide to use the formula, it would have been fine, because that would have become a plus 2d. The a is the first term, so that would have been the 2x. So I would have gone 2x plus 2 times the difference, which is 2, which is 2x plus 4. You can see the answers we get are absolutely identical. So we can think of it as term 2 adding on a difference, or we can go fresh from start and say term 3 looks like a plus 2d. Let's replace our a, let's replace our d. Right, let's have a look at the next one. The next one says, write down the next term in the following, and I see I've made a little bit of an error here, nothing major. It should be geometric sequence. All right, so now if it's a geometric sequence and we've got x, root x, we know it's geometric, that's term 1 and that's term 2. And we know to get the ratio, we can take term 2 divided by term 1. Right, which will be root x divided by x. Okay, so now they're going to make you practice some of your exponents, which is not that bad. One way to do it is to say, well, I know that that's root x, and so this would be root x times root x. That one will divide into that one, and I'm going to get 1 over root x. But probably the more effective way for you would be to say that's x to the half divided by x to the 1. Remember a root sign, if we think back to our exponents, something like that, it would be x to the p over n. Okay, which then gives me x to the minus a half, and we know we don't like to write negative exponents, so we go x to the half, which is equal to 1 over root x. Either way, we've established that that is the ratio. Right, so now at this point, we're going to now go one of two ways again. We're going to use the formula, and we're going to just use multiplying on. All right, what do we know? We know it was x, root x, and we're looking for this term. So that was term 1, this was term 2, this is term 3. So to find term 3, I could take term 2 and multiply it by my r value. Now, if I do that, you can see very nicely that that will cancel, and the answer will be 1. If I use the formula, T3 would take the form of AR squared, where A stands for the first term, which will be x, and my R is my ratio, which I worked out earlier on. So it would become x times 1 over root x all squared. which then gives me x times 1 over x, which cancels and gives me the answer 1. So either way, I get the answer, whether I just do it by taking the previous term and multiplying on, or I use my formula. Obviously, if I had asked you for the 750th term, you're not going to simply work it out by working out every single term, getting the 749th one and then timesing on. That's where the formula comes into its own and becomes very, very important. Let's look at the next example. Now this gets a little bit more exciting. What they're asking me to do here is to determine the 7th term. And you can see that this looks pretty ugly of the following sequence. They don't tell me what type of sequence it is. Now that's where it gets very important. So the first thing you would do, and this is where the flow chart I'll give you later on in the next lesson, will help you, because what you'll do is you'll look at this and you'll say, okay, fine. Let's see if we have a constant difference. You've got calculators. You can pull your calculator up and check that if I take 3 over 32, subtract 1 over 64, what I get. If I take 9/16, subtract 3 over 32, what I get. And if I take 27, subtract 9/16, what I get. But one thing I will find out is there is not a constant first difference or a constant second difference. So that means the only option open to me is to go with a geometric option. So to say, what am I timesing by to get there? So what I'm going to do, I'm going to take my calculator, term 2 divide by term 1. Right, let's pull up the calculator. Okay, we've got a fraction button. Let's put in I must put in 3 divided by 32. And I must divide that by another fraction, 1 over 64. If you don't have the fraction button key, it's not the end of the world. Just do normally, in fact, the next one I'll do normally just to show you how it's done. Press your equal sign. You're going to see that the answer works out to be 6. Now let's check and see that term 3 divided by term 2 results in a similar kind of answer. So as I said, this time I will do it without pulling up the calculator. Let me remind myself it's 9/16. So it's clear. I'm just going to go brackets. 9 divided by 16. Close the brackets. Divided by 3. In fact, let me put the brackets in as well. Divide by 32. And really good news, I've yet again got 6, which means that there is a constant difference. So constant ratio, R is equal to 6 in each case. So we are dealing with a geometric sequence. Notice how I abbreviate it. I use a G and an S, geometric sequence. While we're here, let's talk for 2 seconds about the difference between the word sequence and the word series. It's not a major difference, but there is a difference, and where it becomes important is if they ask you to give the sequence. And if you write the series, then you could lose a mark. A sequence is a listing like this. So you would go T1 semicolon, T2 semicolon, etc., etc. A series is an addition. So it's T1 plus T2 plus T3 plus T4. We are going to get to work with the series a lot more in detail in the second lesson. We might even start to touch on it in this lesson. Right, so now going back to our question, we can see that they want the 7th term. We have established that it's a geometric sequence. Now some people like to do this every time. They go Tn is equal to AR to the n minus 1, and that is fine. But you won't get marks for it because that's provided on the actual formula sheet. So I prefer to say T7 is AR6, and I go straight there because that way I'm ready to go immediately on my working. Now remember, A stood for the first term. The first term in this one is 1/64. R is calculated as 6, so we're going to say 1 over 64 times R, which is 6 to the 6. And as I say, thank heavens we have calculators. It's going to make our lives really quite easy. So we pull up our calculator. So what have we got? We've got fraction button 1 over 64 times by, and we could just use a bracket, 6 to the power 6. Oh dear, that wasn't a good idea. Space bar out, bracket, equals. And you're going to find that the answer of this is 729. Let me just check I wrote that down correctly. Yeah, perfect. Okay, so term 7 is that. Of course, I could have got carried away and asked you for term 1007. Why not? It would have been exactly the same process. You've got a calculator. You're going to get an enormous answer, but I could have asked you that. So relatively easy. Just remember the steps again, just to recap. The first decision I make is what type of sequence. And remember, when I do that, I have a choice of 3. I have arithmetic, we have quadratic, which we've talked about already today, and geometric. And I normally go in that order. So I normally look for my first difference, look for my second difference, then go to the geometric. And yes, I get smart and realize what a geometric looks like. That is the safest way to go. Right, let's move to the next question. The next question says the following sequence of numbers is given: 3, 7, and 11. Is 33 a number on the sequence? Well, there are several ways to find this out. The one way is to have a look at what we've got. We've got 3, 7, and 11. What is happening here each time? Well, here I'm adding 4. Here I'm adding 4. And so, yes, what I can keep on doing is adding 4. So it'll be 15. It will be 19. It would be 23. It would be 27. It would be 31. And it would be 35. Eek, you can see that 33 will not be in the sequence. Now, that's all very well while I ask you something small. But what happens if I said to you, is 3,333 a term in the sequence? Then it wouldn't be such fun. So what we're going to do here is we're going to rather go and find the nth term of the sequence. And then we're going to substitute in this value, because what I'm doing is I'm saying, is it possible for a term to look like that? Now, we've established that it's not possible, but let's just do it as if we are establishing it from scratch. So what do we know? We know that we have an A value of 3 and a constant difference of 4. That's what we know. So now we can go and look for the Tn. Now this time I don't know what Tn is going to be, so I'm going to use the full formula. A plus n minus 1d. Right, so the A is 3. The n I have absolutely no idea what it is, and the d is 4. And what do I know about Tn? Well, I'm saying, is it possible for Tn to be 33? So n is what's missing in action. So I put the 33 there. Right, so let's tidy this up and solve for n and see if that is even remotely possible. So what I'm going to do is you can decide most pupils times this out. You can work without it, so I'm going to go with what most people would do. It's 33 equals 3 plus 4n minus 4. That means that 33 is equal to, and that's going to give me 4n minus 1, which means I've got 33 plus 1 equals 4n, which means 34 equals 4n. Now to find n, I divide both sides by 4. So doing that, I'm going to get n is 17 over 2. Right, we have a problem. What did n stand for? N stood for the number of terms. So can you have a 8.5 term? The answer is clearly no. One thing we must fix in our minds whenever we're working with this is that our n value is always going to be a natural number. Okay, notice how I show the number system with the extra bar, just to distinguish it from the letter n, meaning a point or something like that. So that's how I'm letting you know I'm working with natural numbers. So that is clearly not possible. Therefore, no, it is not a term. Right, let's now go to the next part of the question, which says, write down the first number in the sequence greater than 33. Now, we've cheated. We've already worked that out. It's actually 35. But what they're expecting you to do, if it was a number too big to actually do it physically like we've done it, they would expect you to say, well, look, this was 8.5. So the next one bigger must be the 9th term. So we want to know what term 9 looks like. It's going to be A plus A to D. Notice again, instead of writing T9 equals A plus 9 minus 1D, I went straight there. There's nothing wrong with writing that other step down. It just takes a bit longer, and it's also with more numbers on a page, it always makes it more confusing and more likely to make a mistake. Right, so now we go over here. T9 is equal to A, which we established was 3, plus 8 times the difference, which is 4, which is 3 plus 32, which is 35. And that's what we worked out when we did it longwise over here. So that makes perfect sense. So the next term up is 35. Right, let's move down a little bit and see what the next question says. Okay, now it seems like I've gone ahead and done this question already, because it says find a formula for the nth term of the sequence. And that's what I actually did up here basically, but let's go and do it from scratch again. So Tn is equal to A plus n minus 1d. Now what the nth term is about is it's a formula that enables you to generate all the terms on the sequence without any problem at all. So what I would do is I'd say Tn is equal to 3 plus n minus 1 times the difference, which is 4, which is 3 plus 4n minus 4, which is 4n minus 1. So what I'm saying to you is if I used this formula, I could find any term in the sequence. You would not be expected to do this, but let's just check one. Let's see what term 3 would look like. Term 3 would be 4 times 3 minus 1, which is 12 minus 1, which is 11. And if I look up here, let's see if that's true. Yes, term 3 was 11. So it is working. My formula is perfect. So what's nice about this section, you're actually in a position to check whether your nth term would work for it if you have the first 3 terms or any terms really in the sequence. Let's have a look now at the next example and see what they're going to do with this. This one now involves us knowing about 2 of the terms in the series, or the sequence, depending how you want to look at it, but they've said series, so let's stick with it. And they're asking you to find the value of the first term and the constant ratio. So if we're going to think of it like this, we know that that's term 1, term 2, term 3, term 4, term 5. They've told me that the second term is 1/10, and the fifth term is 27 over 1250. Now, we don't know anything about these ones, so it's not going to be as easy as before to find our A and our R, because we can't just look and say A is, and we can't take this divided by this because we don't have it, or this divided by this because we don't have it. So what they're actually requiring me to do here is a simultaneous equation. Now, the first thing I always do is I code the question. Now, by code, I mean I'm going to write it in mathematics. So they tell me the second term is 1/10. So T2 equals 1/10. And then they tell me the fifth term is that. So term 5 is 27 over 1250. Right, so that's the coding done. The next thing I would do is I would put in my formula. Now, what is a big problem in this kind of section is that people are inclined to use the wrong formulas, and then they can't give you any marks. So make a habit of saying it's geometric, and we're talking terms, so it's AR to the n minus 1 that I'm working with. So the temptation to work with the wrong formula is gone now. You've made sure that you've committed it over there. So how would the second term of a geometric sequence look? It would be AR to the 1. We don't have to write the 1, but I'm going to put it in for the purposes of this explanation. And then term 5 would be AR to the 4 equals 27 over 1250. Now, I said to you earlier on that they're requiring simultaneous equations. So I'd call this equation 1 and I'd call this equation 2. Now, the problem with this is you can see because it's fractions, it's very intimidating. Obviously, if it wasn't fractions, you wouldn't be having any problems with this at all. So you can go the normal route of simultaneous where you find a subject. So I could say to you from equation 1, we could say A is equal to 1/10 divided by R. And of course, that would mean 1/10 times 1 over R, which would be 1 over 10R. But you can see that that can get pretty ugly, especially if it was more complicated than what this was, which is possible. So rather than that, I'm going to show you a really nice technique worth knowing for any geometric simultaneous equation. Now, how it works is if I say to you x equals 4 and y equals 2, could you give me the answer of x over y? Yes, you would. You would say, well, x was equal to 4 and y was equal to 2. And so x over y would equal 2. And we're going to use a similar kind of process to that to work out this particular question. So going back to our question, I'm going to now say, if I look over here, this one's got the bigger powers. So let's take equation 2 and divide it by equation 1. So it's AR to the 4. I'm going to have my equals here, 27 over 1250. And then I'm going to divide it by equation 1, which is AR, and that's going to be 1/10. So literally what I do is I take the left side of this, divide by the left side of that, equals the right side of that divided by the right side of that. Right, so doing that, you can see that the a's will cancel, and I'm going to get r cubed. And this we can use our calculator for, but I'm going to be good and do it manually. Remember, if we're dividing by a fraction, we tip in times, so it's going to become 10 over 1. And if we work that out, we're going to get 27 over 125. Now, if we look at that, we can again use our calculator to get that answer out. But I'm going to be good again, and I'm going to use exponents, because it's always good to revise some of the stuff. So I'd say to myself, in order to solve this, I need to have this to a power 3 and this to a power 3. 27 is 3 cubed, and 125 is 5 cubed. So r cubed is equal to that. So that means r cubed is equal to 3/5 all cubed. Now, since they're both cubed, I could say r is equal to 3/5. Just a little warning here. If this had been r squared equals 9/4, then you must remember that you could write this as 3 over 2, all squared, but you could have had a plus minus in here. Okay, which means in actual fact your r would have been plus or minus 3 over 2. So just be careful with even powers. You can pick up 2 r values. What they normally do in an exam with that kind of thing is they'll say to you all the terms are positive, which means then you can discard the negative one. Or they will say that the sequence has got mixed terms between positive and negative. Right, let's get rid of that because this is not this particular example. Right, so what we've established now is that our r is 3/5. Now, we have to still find our a because the question asked me to find a and r. Now, at this stage, I'd look at this and I'd decide which of these two equations is the easiest one. And definitely equation 1 is the easiest of the two. I know, and let's put this in blue so you can see I'm working on the a, that AR equals 1/10. So A is what I'm looking for. R I know is 3/5 equals 1/10. Now to get rid of the 3/5, I would divide both sides by 3/5. Or what I could do is multiply this side by 5/3 as long as I multiply this side by 5/3. Remember, with an equation, as long as you do to one side what you do to the other side, all's well, because it keeps its balance. So doing that, the 3's will cancel, the 5's will cancel. I'm going to get A. Over here, 5 goes into there once and into there twice, so I'm going to get 1/6. Right, what did the question ask me for? I think if I remember rightly, it just said to me, find the first term and the constant ratio. Have we done that? Yes, we have. What would have happened if the question had asked me to find the first 3 terms of the sequence? Well, that wouldn't have been too bad. What do we know? We know the first term is just A. We actually knew the next one, but if we were going to work it out, we would take 1/6 times 3/5. And if we do that, that goes once, that goes twice. It's going to give me 1/10. So I put down 1/10. And then I would take 1/10 and times it by 3/5 again. And if I did that, I would get 3 over 50. And once I had 3 terms, I would just show a few dots to say this continues. So if they had asked me that, that's what I would have done, and it wouldn't have been such a big problem. However, this question only asked me for A and for R. Lovely little question. Let's see what the next one brings. Right, now the next one introduces me to a sequence where all my terms are given in variables. They tell me that t plus 1, 1 minus t, 2 minus 5t are the first 3 terms of a geometric sequence. Now, I want to stop here for a few seconds and just point out something that, although it seems obvious, is not perhaps that obvious. That obviously, when we are dealing with the geometric sequence, T1, T2, T3, and I said we could calculate the ratio by going term 2 divided by term 1, we could obviously make an equation of this and work. In other words, term 2 divided by term 1 must equal term 3 divided by term 2, since that's giving me a constant difference in both cases. Right, so doing that, this is my term 1, this is my term 2, and this is my term 3. I know that 1 minus t divided by t plus 1 must equal 2 minus 5t divided by 1 minus t. Now, notice the question. It says calculate the value or values of t. So what they're implying to me is that perhaps there's more than one value for t. And usually if they use that S word attached, there is more than one. So let's have a look at what happens. Now, how do we solve something like this? Remember last time when we were doing revision, I taught you that if we have something like this looking at us, and we times both sides by the LCD, we're going to get AD equals BC, or cross multiplication. So what I'm going to do is I'm going to times those, and I'm going to put it equal to those times. I can do it because it's a fraction equals a fraction. Right, so doing that, I've got 1 minus t times 1 minus t equals 2 minus 5t times t plus 1. Good, so now we're going to get to practice our distributive law. And so we're going to say that times that is 1, that times that is minus t, that times that is minus t, and that times that is plus t squared. That's equal to, again, distributive law, it's going to be 2t, that times that is going to be 2, and that one times that one is going to be minus 5t, and the last ones times together, wait, I think I've left one out, let's just go back, 2 times t, 2 times 1, minus 5, yes, I left that one out, is minus 5t squared. So this one here is there. Right, I can see that I've got an expression, and it's a quadratic expression, which means I would actually try and get everything on one side and then sort it out from there. So doing that, I would say 5t squared plus t squared. Here I've got minus 2t, and over here I've got minus 3t, which comes over as plus 3t. And there I've got a 1, and I'm going to bring that over as a minus 2 equals 0. You can be more cautious and do this more gradually, but I think that's fine. I think you've had enough practice in your lower levels, and I'm sure you feel confident with it. So 5t squared plus t squared is going to be 6t squared. If I add these guys, I'm going to get plus t, and if I add those ones, I'm going to get minus 1 equals 0. Right, wonderful. Now we're going to look at it, and we're going to factorize it. So 3t, 2t, 1, and 1. I want to get a plus on the bigger one and a minus on the smaller one. And so my t works out to be 1/3, or my t works out to be minus a half. Right, going back to the question, if it'll let me, it doesn't say anything at all about whether these terms are all positive or these are all negative. So in that case, we have to work with both. And I think what I was going to do over here is calculate the value of the common ratio if the terms are all positive. However, if I hadn't put that stipulation in, you would have done both of them. Now, if we look at this, we have to first of all go and look at what our terms look like. We have got two possibilities for t. The actual sequence was t plus 1, 1 minus t, and 2 minus 5t. So if we go with the first one, where we're going to put in 1/3. 1/3 plus 1 is 1 1/3, or if you like, 4/3. It's always easier to work with fractions that are top-heavy because they're easier to follow when you're doing subtracting and that. Now it's 1 minus 1/3, which will give me 2/3. And this one is going to be 2 minus 5 times 1/3, which is 2 minus 5/3. And if we put that over a common denominator, it's going to be 6 minus 5, which is going to be 1/3. Now, if we look at this, do you agree with me that all the terms are positive? So this is probably the one they want me to work with, but let's make sure and work out the other one. Now, in this case, if t is minus a half, we've got minus a half plus 1, which is a half. The next term would be 1 minus minus a half, which is also positive. So look at that. In actual fact, both of them are working out to be the same. So I couldn't have taken a good guess on this. And then this one is 2 minus 5 times minus a half, which is 2 plus 5 over 2, which is equal to, and if we put it over 2, 4 plus 5, which is 9 over 2. So it's 9 over 2. So good news for us, and of course the calculator could help you with all this arithmetic I've been doing, but I've decided to do one question where I don't rely on the calculator so much, and I'm sure you know what that feels like. Right, so now once we're here, they ask me for the common ratio. Now how do we get the common ratio? We get it by saying term 2 divided by term 1. So if we go over here, we're going to say 2/3 divide by 4/3, which will be equal to 2/3 times, so we invert and multiply this bottom fraction, 3 over 4. The 3's divide into each other. That goes once, that goes twice, and I'm going to get a half. So when t was 1/3, I think it was 1/3, let me just make sure about that. Yes. R is equal to a half. But this other one is also possible. So what I'm going to do here is I'm going to say R is equal to 3 over 2 divided by a half, which is going to be 3 over 2 times 2 over 1, inverting and multiplying. That goes once, that goes once. It's going to give me 3. And so if t equals negative a half, the R is equal to 3. And as we've seen, both of these make sure that our sequence has got all positive terms. So it was almost like a trick in this question because they were anticipating you saying, okay, well, if t is minus a half, then the terms are not going to be positive. But it so turns out that they are. Lovely little question, get you to think a little bit. Right, next question. They say, consider the following sequence, 1, 2, 3, 4, 5, 6, 7, 8, 9, so on to 41. They ask you to write down the next 3 terms after 9. Now, all you have to do is establish what kind of thing is going on here. So let's take our blue pen and mark it in. What's happening to move from here to here? We are adding 1. To move here, adding 1. Here, adding 1. Here, adding 1. We can be pretty sure that's how this term is behaving. So after 9, the next term would be 10. The next one would be 11. And the next one would be 12, etc. Now, this is a very easy question. And I've deliberately chosen easy because this way I can show you that the formulas are working. Whereas if I chose numbers that were too big and too huge, it would be hard for you to see that these formulas are actually doing their job. Obviously, if we're starting at 1 and ending at 41, how many terms are we going to have? We're going to have 41 terms. So what I'm going to do now is I'm going to say, I want to find out how many terms. So let's say Tn equal 41. Now, what does Tn look like? Well, what type of sequence is this? I didn't even go there. It's arithmetic. Every time we have a constant difference of 1. So the d is 1, our a is 1, and so the term would be a plus n minus 1 d equals 41. So 1 plus n minus 1 times 1 is 41. Right, let's tidy this up and get our answer. So 1 plus n minus 1 is equal to 41. 1 minus 1 falls away, so n is equal to 41. And so we can say there are 41 terms in the sequence. Now, of course, we knew that already. Just to show you that this would work on a more complicated one, let's take something like this, 2, 5, 8, and say I say to you how many terms in that sequence. Now, obviously, you can see this is not so easy to tell. So the first thing I would do is I'd say A is 2. My difference each time is 3. My nth term is 308, and I want to find n. So my formula Tn is equal to a plus n minus 1d. All is well with this formula because I have got this, this, and this, which leaves me with only one more thing to find. So I can say 308 equals 2 plus n minus 1 I don't know, and the difference I know is 3. Notice I'm making a habit of putting a bracket there. The reason why is if it had been negative 3 and you wrote n minus 1 minus 3, you could get confused later on and not realize that you're actually multiplying and think it's subtraction. So rather make a habit of using brackets on your substitution. It's just a little bit safer. Right, so back to this question then. We have 308 equals 2 plus 3n minus 3. That means that 308 equals 3n minus 1, which means 309 is equal to 3n, which means if we divide by 3, 103 is equal to n. So there are 103 terms in this sequence. So you can see with a harder question, it's not a problem if you use the procedure, but it's quite important looking at an easy one that you can be sure in your mind that this will always work. Right, let's look at another question. This one says the second and the fourth, spelled incorrectly, I do apologize, F-O-U-R-T-H, term of a converging geometric sequence are respectively 36 and 16. All the terms are positive. Remember I said to you that's what they're going to do if they have any worry going on this whole story. So right, looking at that, remember I said to you the first thing we do is we code. Now they want the constant ratio. The constant ratio is found by taking two consecutive terms and dividing the one by the other. We don't have two consecutive terms, so here we go with our coding. So we're going to say T2 equals 36 and T4 equals 16. Term 6 will take the form of, term 2, will take the form of AR equals 36, and term 4 would be AR cubed equals 16. This would be equation 1, this would be equation 2. So I've coded, I've put the formula in. The next thing I'm going to do is I'm going to use simultaneous equations. So I'm going to take equation 2, divide by equation 1, so it's AR cubed divided by AR equals 16 divided by 36. The A divides into the A, so I get R squared equals, and I can see 4 will go into there 4 times, and 4 will go into there 9 times. And here's the case I mentioned earlier, that we've got R squared, which means R is plus or minus 2/3, because we take the square root, but we introduce the plus minus. However, they told me all the terms are positive. Now, if you have an R that is negative, can the terms be all positive? Obviously not, because the positive times the negative will give me a negative, and so it won't work. So I can know that the only R I'm interested in, because it's the positive, is the positive 2/3. All terms positive. Right, the next question says, find the first term. Well, again, what did we do? We went to our formula that was the easiest, equation 1, and I substitute R in. So it's going to become A times 2/3 equals 36. This time, I'm going to show you how to do it not by timesing by the reciprocal, but by the normal way, which means divide by 2/3, divide by 2/3, and so we're going to get A, because that one will divide into that one, equals 36 times 3/2. That goes once, that goes 18 times, and 18 times 3 is going to be 4 carry the 2, 54. Okay, that's all they asked in the question, and it's relatively easy. You've got your A and you've got your R. So quite easy, quite straightforward. Now you've seen this technique of doing our simultaneous equations. Right, let's have a look now at what would have happened if I'd been given two terms of an arithmetic sequence. How would that have differed from the previous one? Well, let's suppose I say to you term 6 is equal to 16 and term 10 is equal to 36, and it's an arithmetic sequence. Now, as soon as I hear that, I know I'm working with the formula Tn is a plus n minus 1 d. Right, so term 6 is going to be a plus 5d equals 16, which we call this equation 1, and a plus 9d equals 36, and we call this equation 2. Now, obviously, with these ones, it's a normal simultaneous equation. And so you could go the elimination method or the substitution method. Quite honestly, I think you're better off with elimination because you can see if I write these underneath each other, so if I put the bigger one over here, equation 2, and underneath I write equation 1, which has got smaller numbers in it, and I say, let's take equation 2, subtract equation 1. You can see if I'm going to take a and subtract a, it'll fall away. 9d minus 5d will give me 4d. And 36 minus 16 would give me 20. Now, you might say, well, what happened if I did it the other way? Well, it wouldn't have been the end of the world. All that would have happened is you would have had a negative here and a negative there. And it would have crossed itself out when you had the negative over a negative. So dividing both sides by 4, our d is equal to 5. Right, that's wonderful. Now we know what d is. We need to go back for a. Once again, I would select the easiest of the two equations. So from equation 1, which is a plus 5d equals 16. Let us substitute d equals 5. Notice that I am making an effort, wherever possible, to tell my marker what I'm doing. This helps them to see how you're thinking, and if you do make a mistake, they can say, well, look at that, the logic is right, but by mistake, they made an arithmetic error. So I can give them method marks. And it's always good to have those method marks if you make arithmetic errors. So it's a plus 5 times 5 equals 16. So a plus 25 equals 16, which means a is 16 minus 25. Now, if I take 16 minus 25, I get minus 9, and so I've got a. So if I'd asked you for a and d at this stage, you would have done it quite easily and left yourself at that. But I think we should just generate the first 3 terms. So if the first term is minus 9, how do I get to the next one? Well, if it's arithmetic, I add 5. So the next term will be minus 4. To get to the next one, I'd add 5 again, so it would be 1. And if I wanted to just be sure for one more, add on another 5, giving me 6. And that would be adequate to show them I knew how to find this particular sequence. Right, now what I'm going to do is I'm going to start to introduce the sum of an arithmetic and the sum of a geometric series. It's actually quite interesting, really, because how this whole field of mathematics came about was there was a mathematician called Gauss, and at that stage he was at school. He was extremely bright, and he was driving his teacher insane. And the teacher said to him, go away and add up the numbers from 1 to 100 and then come back. And the teacher thought to himself, well, at least that gets rid of him for a while. Unfortunately, he was back like a flash with an answer. And a whole field of mathematics, which is what we're doing here, came about. Let's show you how he did this. It was quite a clever feat for a young boy. By the way, just for a matter of interest, most mathematicians do most of their great work when they're youth. So it's up to you guys. Right, let's have a look at this. Let's go to Gauss's problem. He was told to go and add up all the numbers up to 100. Now, we might say to ourselves, well, you know what, that's not very difficult. That's actually very easy. We just take our calculator and add it up. But he was not privileged to have a calculator like we have, so he had to use his mind. This clever boy actually managed to see the following. In fact, what I'm going to do is make it a slightly smaller. No, I'm going to leave it like it is. I think it's quite interesting to actually see how clever he was. Okay, do you agree with me that if I take 3 terms at the start and 3 terms at the end, I can see it? Now, do you agree with me if I take 2 plus 3, I'll get 5? And if I go 3 plus 2, I will still get 5. It'll make no difference to me which order I add it in. So what he did is he said, okay, fine, let's say 100 plus 99 plus 98 plus 3 plus 2 plus 1. And he knows that that blue sequence, or series rather, will give him exactly the same answer as the black series. All right, then he said to himself, well, let's look at this. What's interesting is if I add this, I'm going to get 101. And if I add this, I'm going to get 101. And if I add this, I'm going to get 101. And this is going to carry on all the way along here. Now that was a great discovery he's just made. So he's seen that every single time 101 gets added up. Right, so how many 101s will we have? Well, there are 100 terms. So we've got 100 times 101. But do you agree with me that we've actually added the sequence twice? So we would have to divide it by 2. I'm going to use the symbols S because that's what we do for it. And we would say S100 because we're adding 100 terms. You'll see more details on this in the next lesson, but just to get us going. So that goes once, and that'll go 50 times. And 50 times that is going to give me 5050. And that's why he was back in a flash to his teacher. And much to the teacher's horror, a whole new field of mathematics was born. And it's quite amazing you think that a young boy can do that kind of thing. So it just shows you it's definitely up to you. Let's now develop the formula properly. Because I've just shown you a numeric example, and I would like to show you now what he actually did. What he did is he said, let the nth term equal L, where L stands for the last term. So what he did is he said, right, if I'm going to add up n terms, I'm going to start, and the first term will just be A. The next term will be A plus D, because we know that's how they look. The next term will be A plus 2D. And I'm adding them, so I'm putting the add signs in. And I'm going to keep on going till I get to the other end, which is the last term. What would the term before that be? It would be last minus difference. And the term before that would be last minus twice the difference. Let's just make these blue so we separate our terms clearly. Now, what did Gauss do? He then reversed the order. So he said, okay, fine. Let's keep this running exactly the same way, and let's reverse our order. So he went L minus D, L minus 2D, dot, 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 A plus 2D, A plus D, A. And he said, that's still Sn, which it is, just in a different order, but the same thing. He then added these, so he said, I've got 2 lots of S to the N. And let's see what's happening here. Well, if I add those, I'm going to get A plus L. If I add those, the D's are going to fall away. I'm going to get A plus L. If I add here, again, the 2 D's falling away, A plus L. And all the way along here, I'm going to have A plus L. Let's separate them with plus signs so we can see them clearly. Right, so how many lots of A plus L's will he have? Well, there were n terms. So there must be n lots of A plus L, which means Sn is equal to n over 2 A plus L. Now, I can hear you thinking, and you're thinking to yourself, this is not possible to do it like this. Well, let's talk about it. If I've got 2S equals 4 times 10, S would equal 4 times 10 over 2. Do you agree with me that would be 40 over 2, which is 20? Now, if I do it like this, where I just divide the 4, do I get a different answer? Well, the answer is no, because 4 divided by 2 is going to give me 2 times 10, which also gives me 20. So what I'm doing here is quite legal. Now, over here, I've got Sn equals n over 2. I've got A, but what I'm going to do now is I'm going to replace that last term with Tn. So, Sn is equal to n over 2, A plus, and in place of Tn, we can write A plus n minus 1d. And we can close our bracket. Right, now sort of adding like terms here, we can say n over 2. This gives me 2a plus n minus 1d, like that. And if you look on your formula sheets, you will see this formula. Unfortunately, it's shown on the other side of the sigma notation, which we're going to deal with in the next lesson. So you would have this looking at you. Now, we could use this format of the equation as well as this one. This one is useful if we know the last term. However, we don't often know the last term. Right, so let's go now and have a look at what happens if this is a geometric sequence. And I'm not going to waste time doing numeric example. I'm going to go straight into the formula because you've seen how nicely it comes out with it. So if I'm going to sum in terms of a geometric sequence, the first term would be A, the next term would be AR, the next term would be AR squared, and this would carry on to my last term, which is term N, which is AR to the N minus 1. Notice I'm going to put in my plus signs here in a different color, so I stress the terms are different. Now, what happened with this one, we could not just reverse the order. So what we did is we said, let's times R by Sn. Now, if I'm going to do that, if I times R onto A, do you agree with me? I'm going to get AR. And if I take AR and I times by R, I'm going to get AR squared. And when I take this and I times it, I'm going to get AR cubed. Obviously, this one, if I've got AR to the N minus 1 times R to the 1, the rule says I write down the base and I add my exponents. So it's N minus 1 plus 1, which is A times R to the N. So doing that, this term is going to move over here. So in actual fact, each of these have slid 1 along, which means the 1 over here would have produced the AR to the N minus 1. Let's put our plus signs in again, and then we can discuss what is going to happen here. Right, so what we do now is we subtract these two. Why subtract? Well, if we subtract them, we actually lose this middle section. So we're going to get Sn minus Rsn. Do you agree with me? I can't actually do the subtraction there because they're not like terms. Now over here, A minus nothing gives me A. This will fall away, this will fall away, this will fall away, and all of these will fall away till I get here where I have nothing, subtract that, which is AR to the N. Now if I look over here, I could take Sn out as a common factor, giving myself 1 minus R. And over here, I could take out A as a common factor, giving myself 1 minus R to the N. That means that Sn could be seen as A, 1 minus R to the N over 1 minus R. And if I look at that, that's really good, except in one case, do you agree with me that R may not equal 1? Now that makes perfect sense, because if R did equal 1, so in other words, we had the first term of 2, what would the next term be? It would also be 2. And the next term, also 2. And the next one, also 2. And so it's a pretty trivial kind of pattern. And if I asked you for 50 terms, you wouldn't waste any time using a formula. You would just say 50 times 2. So there's no problem with the fact that we can't have R equal to 1. Right, so now looking at this now, what else could we do to it? We could say, let's take out a negative. If we do, we've got R to the N minus 1. And if we take a negative out of here, we've got R minus 1. Right, that means that this formula would become A, R to the N minus 1 over R minus 1. And once again, the R may not equal 1. Now you might say, well, why do we need two formulas? We don't really need two formulas. We're actually quite happy with one of the formulas. But sometimes it's actually expedient to have the one over the other because it avoids you working with lots of negative numbers. So how would we know which to choose? I would choose to use this one, yeah, the black one, if R was less than 1. Think about it. If R was 2, I would have a problem. I'd have 1 minus 2, which would give me negative 1, not nice to work with. But if R was negative 4, I'd have 1 minus minus 4, which would make this a positive, and a denominator that's positive just easier to work with. And over here on this one, I would work with it when R is greater than 1. Using our same example, if I take 2, 2 minus 1 would be nice, but if I had minus 4 minus 1, I'd have minus 5, which would be quite mean to work with. Right, that brings us to the end of this session. I am going to assume that we know this for when we move on to our next lesson. So just remember the formulas, and we will stress them as we go, but I will not prove them again. So thank you very much for joining us, and we look forward to us joining ourselves in the next lesson.